Hello everyone, this is Dennis and you are on the Electro channel. Today I will show you how to make such a compact 20-watt power supply. The output voltage is 5 volts and the maximum current is 4 amperes. The topology of this power supply is flyback. The efficiency is very high and at idle it consumes only 8 milliamps. This power supply has enough power. It is enough to charge huge power banks. For powering cell phones that consume a current of about 2 amperes or for powering devices that charge portable batteries. The heart of the power supply is the CR6850 PWM chip. I will explain in detail how it works, how the power supplies on its base are arranged, and at the end I will provide a test. The power supply circuit looks like this. There are many different details in it. Now I will go over some of them, show how they look and tell you why they are not needed. At first it may seem that the scheme is very complicated, but I assure you it is not. On the left in the diagram we supply an alternating mains voltage of 220 volts. And on the right at the output of the power supply we get stabilized 5 volts. The mains voltage is supplied to the dual choke L1. This choke is called common mode, since it protects against common mode interference. There are 2 identical windings wound in the same direction. AC current flows freely through them, and common mode noise is resisted. C1 is a 100 nanofarad, 275 volt capacitor. They are also called CX-type capacitors. They protect against differential interference. They are usually yellow but are found in blue and brown. Together with the inductor L1, this capacitor forms a noise filter. If someone does not have these details, you cannot put them. The power supply will function perfectly without them, but interference from its operation will fly out to the network. D1, D2, D3, and D4 are 1N4007 silicon diodes. They withstand a voltage of 1000 volts and a current of 1 ampere. C3 is a large 33 microfarad, 400 volt electrolytic capacitor. It smooths out ripples after the diode bridge. After the diode bridge, the amplitude value of the voltage of 310 volts will be used. Therefore, the capacitor must be taken with a voltage margin. The capacitance of such a capacitor is usually read from the output power. 1 microfarad is used for 1 watt. My 20-watt power supply is supposed to be 20 microfarads, but I took a little more at 30 microfarads. The main thing is that the capacity should not be less. Further interest is the resistor R4. Its resistance can be taken from 800 kilo ohms to 2 mega ohms. This resistor is needed for a smooth start of the microcircuit. Look more carefully. The current passing through the resistance gradually charges the capacitor C5. When the voltage on the capacitor reaches 15.3 volts, the microcircuit will turn on and start working. The greater the capacitance of the capacitor and the greater the resistance of the resistor R4, the longer the soft start time. After the power supply starts working, the microcircuit will be powered from the transformer winding. Current from the resistor will flow, but very small. From the power winding, the microcircuit can be powered by any voltage starting from 11 volts. But since the voltage on this winding is not stabilized, it will grow in proportion to the load on the power supply. If the voltage reaches 25.5 volts, then the microcircuit will begin to reduce the length of the pulses, and the power supply will go into protection mode. Q1 is a powerful field effect N-channel transistor. He has a marking of 2N60. Designed for a voltage of 600 volts and is able to withstand a current of 2 amperes. Power dissipation is about 45 watts. Resistor R5 and capacitor C4 make up the snubber circuit. It is needed to absorb the parasitic surge that occurs in the primary winding. If it is not there, the transistor can break through with a high voltage pulse and it will burn out. I wrote here two options for parts that can be supplied. Either a 91 kilo ohm resistor and a 1 nanofarad capacitor, or 43 kilo ohms and a 2.2 nanofarad capacitor. I set myself the first option. Capacitor for 1 kilovolt, but you can take 630 volts. So we got to the most difficult part of the power supply, the T1 transformer. It contains 3 windings: primary, secondary, and microcircuit power supply. The black dots mark the beginning of the windings, and the numbers I mark the ends of the windings. The primary winding consists of 2 semi-windings, each of which has 100 turns. The microcircuit power winding contains 20 turns. There are 9 turns in the secondary winding. I will take the core for the transformer from the ballast of a 30-watt fluorescent light bulb. It is attached to the board and therefore must first be unsoldered. Soldering such elements is easiest with the help of such a desoldering pump. First, press the piston, press the nose against the tin and press the button. Under the action of a spring, the piston flies out and draws in the molten tin. If you would like to purchase one, the link is in the description. A tightening tape is wound on the core. Cut it with a knife and remove it. As you can see, the halves of the core do not fall out and do not even move. They are glued with epoxy glue. You can use a sharp knife to separate them, but this does not always help. In such hopeless cases, I use my method. In the microwave, I heat the water, bringing it to a boil and throw the core into it. The water immediately starts bubbling. Thanks to the ceramic mug, the temperature is very high. Close the lid and leave for 5 minutes. Then, using a spoon, take out the core. Don't forget that it is still very hot. We press the knife into the joint and easily separate the halves of the core. We take out the core from the frame and carefully examine it. The middle column is shorter than the others. So the core has a gap, which is what we need. You see the dimensions of the core on your screens. The gap is approximately 1 mm wide. This gap is called non-magnetic. It is also often referred to as an air gap. The inductance of the primary winding and the output characteristics of the power supply will depend on it. We rewind the throttle wire onto a bobbin from threads. It will still be useful to us, so we do not remove it far. If traces of glue remain on the frame, they must be removed. Please note that the frame has only 4 legs. And we need to make 6 conclusions. When winding the windings, you need to be very careful. And don't forget to count the turns. First, we will wind the primary winding. As I said, it contains 200 turns, but first we will wind only 100. For winding, I use a previously wound occasion. We start winding from the left leg. We lead it to the right, winding up behind the frame. After the wire comes out on the left, bend it to the right. Thus, the first turn will be obtained. In the same direction, we wind another 99 turns. We do not bite off the wire, but temporarily wind it on the right leg. Then we make 2 or 3 layers of insulation using mylar tape. Then we turn the frame on the other side. This will be the side of the secondary winding. I will use the reason for the secondary winding like this. Its diameter is approximately 0.5 millimeter. I folded his second and started winding from the right leg. I went around the frame from right to left and got 1 turn. Then we also do 8 more turns. After the wire comes out on the left, solder it to the leg. In the diagram, these outputs are marked with numbers 5 and 6. Then more isolation. Then we turn the frame again with the side where we wound the primary winding. Let's take the wire from the throttle again, apply as shown in the photo, and make 1 turn. This will be the power winding of the microcircuit. In total, 20 turns must be made in it. We remove the end of the wire to the right up. These ends will be marked 3 and 4. Again, we make 2-3 layers of tape. Then we take the end of the primary winding, which we left on the right leg. On the right, we start it by the frame and display it on the left. This will be a continuation of the primary winding. Repeating the operation, we make another 99 turns. We wind the end of the wire on the right leg and bite off. Let's take a look at 1 and 2 here. All transformer windings are ready. It is not necessary to wind the outer insulation. I made it only for beauty. Then we take the core and insert it into the frame. Tie the halves tightly with ribbon. Otherwise, the core will hum during operation. We connect the primary winding of the transformer to the tester of radio components. The inductance we require should be from 2,200 to 2,200 microhenries. And I got only 1850. In general, the transformer will work on the resulting inductance, but will produce less power. So I decided to remake the transformer. To correct the situation, it is necessary to reduce the air gap between the halves of the core. This will increase the inductance. Take a closer look at the transformer. As you can see, the core has a slight backlash. He dangles in the frame. That's what we need. To reduce the air gap between the halves, you need to take a file and grind off the side posts of the core. The halves will fit tighter, and the gap will decrease. After filing with a file, the gap became 0.6 millimeter. Let's see what we got. And it turned out more than necessary, 2380 microhenries. This is a small error and it is quite acceptable. From the secondary windings, current flows to the diode assembly. It contains two Schottky diodes. They have a small voltage drop, they heat up less, and therefore the efficiency of the power supply is higher. The cathodes of the diodes are connected and the anodes are independent. This assembly is rated for 20 amps and 100 volts. In this circuit, I connected the anodes of the diodes so that they work in parallel. L2 is a throttle. For its manufacture, I used a ferrite dumbbell of the indicated dimensions. The wire was used as in the secondary winding of the transformer. I made 10 turns of a double core. The inductance should be about 10 microhenries. Such a small inductance convenient to measure with a homemade device. As you can see, I calibrated it to 8 microhenries. And then I checked the assembled coil. Its inductance turned out to be about 12 microhenries. This is a little more than necessary, but a slight deviation is acceptable. Capacitors C8 and C9 are the output filter. They will smooth out the pulsations. Capacitors here must be taken with low internal resistance. This is especially true for the C8. It is located immediately after the diode assemblies and almost all ripples will fall on it. Although the voltage at the output of the power supply is only 5 volts, it is better to take capacitors with a margin. Usually such capacitors can be taken from computer motherboards. The film on their case has a golden color and is easy to distinguish. The high output current of the power supply can also affect the heating of the capacitors. They have to instantly charge and discharge, giving enormous power to the load. To prevent the capacitors from exploding due to heating, it is allowed to add more capacitors. For example, another capacitor can be placed in parallel with C8. The capacity of both can be taken at 470 microfarads. The load on them will decrease, and they will heat up less. Only on the board it will take up more space. C2 is a 10 nanofarad ceramic capacitor, labeled 103. R1 is a very useful resistor. It is responsible for generating the purity of the microcircuit. In the datasheet it is called the resistor. There you can also find a graph of the dependence of the frequency on the resistance of the resistor. If you want to more accurately calculate the purity, then there is a special simple formula for this. For example, I used a resistance of 100 kiloohms, which means the frequency of the power supply is 65 kilohertz. Next comes the U1 chip CR6850. It is made in DIP 8 case and has 8 legs, although the third and sixth legs are not used. The first leg is called the gate. It sends a signal to the gate of the transistor. The second leg of VDD. Here comes the power from the transformer winding to the microcircuit. Fourth leg, sense. The measuring current shunt is connected here. I will talk about it a little later. A resistor is connected to the fifth leg. The seventh leg is called FB, feedback. The optocoupler is connected here. The eighth leg is earth. Here are brief recommended specifications from the datasheet. To power the microcircuit, use a voltage in the range from 11 to 20 volts. In my case, the power winding is just designed for 11 volts. Resistor can be used from 65 to 130 kilo ohms. Working temperature from -20 to 85 degrees. The recommended power of power supplies using this microcircuit is up to 60 watts. But if you want, you can squeeze out the power 3 times more. Purity is recommended to be used from 50 to 100 kilohertz. We return to the circuit again and look at the resistor R6. Its resistance is 1 ohm and its power is 1 watt. In the circuit, it acts as a shunt. When current flows through it, a voltage drop occurs, and the microcircuit measures this drop. This is how overload protection works. If the voltage exceeds the allowable rate, the microcircuit reduces the length of the pulses to the transistor gate, and the total voltage on the power supply sags. Let's explain in more detail in this simplified diagram. Let's say we have a power supply designed for a power of 15 watts, and all the details in it are designed for the same power. If you connect a load of 10 watts, then current will flow through both windings. The microcircuit will measure the voltage drop, but since the drop is small, it will not give a shutdown signal. If you connect more light bulbs, then almost all parts of the power supply will have a hard time. Transistor, diode bridge, and output diode. The transformer windings and the core itself will also heat up, and this is already very bad, since ferrite changes its properties due to heating. Ideally, when the load is large, the current will increase to the calculated limits, and the power supply will go into protection. But in practice, everything turns out to be a little more complicated. The shunt resistance has to be calculated from the maximum power of the power supply. But its resistance is so small that the difference is tenths or even hundredths of an ohm. It is not always possible to find the right resistance, since resistors can have deviation. In general, if you want to make accurate overload protection, then you will have to select the resistance. And if not, then you can set the resistance to 1 ohm like mine. Do not wait for the power supply to go into protection, but simply take more powerful parts with a margin, as they say. And then monitor what load you connect to the power supply. I would also like to add that these figures have nothing to do with reality. I came up with them purely as an example, and you don't need to take them for power supply calculations. Go ahead. PC817 is used for feedback between the secondary winding and the CR6850 chip. C6 is a blue 2.2 nanofarad capacitor, labeled 222. C6 is a blue 2.2 nanofarad capacitor, labeled 222. This capacitor connects the grounds of the primary winding and the secondary. This helps to avoid high-frequency interference from the primary winding to the secondary. Such condensates are of type Y1 and Y2. The function they have is the same difference only in the operating voltage. In our case, absolutely anyone will do. The last detail I want to talk about is the TL431 chip. This is a controlled Zener diode that can be adjusted to any voltage. Stabilized voltage is selected with resistances R10 and R11. The breakdown voltage is found by this formula. In my case, it's easy to calculate. 3.9 divided by 3.9 is 1 plus 1, there will be 2. and we multiply this by the reference voltage of the microcircuit of 2.5 volts. It turns out 5 volts, voltage stabilization. TL431 is also involved in the feedback circuit, and the stabilization of the output voltage of the power supply mainly depends on it. The power supply consists of all these details. It remains only to assemble it. I will assemble the power supply on such a homemade board. It is done quickly and simply. On the printer, print out the wiring of the board and stick it on thick cardboard. On the top side, for convenience, I printed the location of all elements. In the places marked with dots, using a large, thick needle, you need to make holes for the parts. First, I recommend installing a transformer since it is located in the center, and then it will be inconvenient to mount it. And besides, this is the most complex detail. It has 6 conclusions. Then we take the rest of the required parts and assemble the power supply as a designer. The power supply turned out to be nice, convenient, compact, and looks almost like a factory one. On the diode assembly during the testing of the power supply, I screwed a cool, shiny heatsink. From below, I connected all the details with wires. Then I soldered the power wire and wires for the output voltage. I connected 3 USB connectors to them. Always turn on the power supply for the first time through the safety light. If you soldered something incorrectly in your power supply, then with such a connection there will be less chance of burning something. If a short circuit occurs, the light will turn on, and many components of the power supply will remain intact. If after turning on the power supply successfully started, then I recommend idling it for at least 10 minutes. After that, pay attention to the heating of the parts. Everything must be cold. It's time to check what the power supply is capable of. First, I will connect the LED lamp. Works great. Well, then I will connect 3 phones. Each of the phones while charging consumes maximum current is about 1 ampere. The power supply still has plenty of power. You can connect some huge power bank. Now I will connect the power supply to the electronic load and see how the voltage sags under load. I showed how to make an original electronic load on LM317 chips in one of the previous videos. If someone is interested, the link will be in the upper right corner and in the description. By rotating the regulator, I increase the load on the power supply and the current slowly increases. From 5.1 volts, the voltage dipped to 4.9. But this is not the whole power of the power supply. 20 watts is the working load. You can add another 10 watts if needed. With a current of 6 amperes, you can use the power supply, but keep in mind that the windings in the transformer will get very hot. If you load the power supply above the norm, then the voltage drops to 3 volts and the current is almost 9 amperes. I want to add a little more to everything that has been said. If your common mode choke gets very hot during operation, then no one forbids you to disassemble it. Unwind the wire, fold it into 2 or 3 layers and rewind it. The main thing is that the number of turns in the windings is the same. The wire will become thicker, and the inductor will heat up less. The same goes for the transformer. If there is space left on the frame, the wire can be taken thicker and the winding will heat up less. The output choke can also be rewound with a thicker wire, or fold it several times. If something somewhere is heated, then there are losses. Useful electricity turns into heat, and we do not need it. We need maximum efficiency. The transistor and the diode assembly can be put on one radiator, and will not close anything in this case, since their cases are made of plastic. I uploaded the PCB layout file made in the layout range to the cloud. The link will be in the description. If someone has never used this program, then I will explain. When you open the file, you will see a drawing of the board. It is located in the same way as if you were looking at the board from above. All elements of the power supply are drawn in red. You can enter each of them with 2 clicks and there will be its description. We see the green paths as if through the board. Before you print the board, you need to mirror it. At the top of the board from the side of all elements there are 4 jumpers. I marked them in white. Also on the board, I marked the holes where all the outputs of the transformer are inserted. If something is unclear to someone, ask questions in the comments. If you just liked the video, click on the like and also write about it in the comments. If you haven't subscribed to my channel yet, be sure to subscribe. That's all for now, everyone.